Okay, our recent friends, the shaded area problems. We're going to do a real straightforward problem here. This one is about as friendly as you would expect or hope, I guess. Find the area of this region R, which is bounded between these two graphs, root of x and x over 3. So root of x, of course, you should recognize is this guy I'm highlighting in blue, and x over 3 is y equals 1/3 of x, has a y-intercept of 0, and a slope of 1/3 is that guy. So I'll highlight him as red, and the blue guy is G. Find the area. So enclosed region, so it's pretty obvious. It's enclosed between x equals 0 and x equals 9. So our straight up formula for this is we're going to integrate upper minus lower, or further minus closer. So it's going to be g minus h dx, because we're going across the horizontal axis here, from 0 to 9. So I just need to translate that into specific functions, 0 to 9 of root of x, which is g, minus x over 3, which is h dx. Sometimes if these are really crazy functions, they might just say write but do not evaluate the integral expression that would give you that area. This one we're going to have to do. So reminding ourselves that this is the integral from 0 to 9 of x to the 1/2, so we write it as a power function, and 1/3 of x dx, we can now perform the integration. X to the 1/2 is going to become x to the 3/2 divided by 3/2, which is like multiplying by 2/3, minus 1/3 x is going to become x squared divided by 2, but we've already got a 3 down there, so it's going to be 1/6 of x squared. And we're going to evaluate that between 0 and 9. Very nice to have perfect squares as our limits because we're taking square roots. Very, very nice to have 0 as our lower limit because that is just going to go to 0. So we're going to substitute 9 in, 2/3 of 9 to the 3/2 minus 1/6 of 9 squared, minus what we get when we plug in 0, which of course is just going to be 0, but I'm going to write it for posterity's sake anyway. 1/6 of 0 squared. So that of course is going to go to 0, but here we have 2/3 of 9 to the 3/2, which is the square root of 9, which is 3, cubed, which is 27. So that's 2/3 of 27 minus 1/6 of 81. 2/3 of 27 is 27 divided by 3, which is 9 times 2 is 18. You say, I don't know what 81 divided by 6 is, but 81 is 3 times 3 times 3 times 3, and 6 is 2 times 3, so you can cancel out those 3's, and it's going to be 27 over 2. To get a common denom, that's 36 over 2 minus 27 over 2, which is 9 over 2. And there is our area bounded by those two curves between 0 and 9. All right, inevitably they're going to have you do a volume. Whether it is a volume with cross-sections where you use the region as the base of a solid, we've done a few of those, or a volume of revolution that we get where we take this thing, revolve it around an axis and get a solid. That's what we're going to have here. Revolved around the horizontal line y equals 4. So I took the liberty of kind of bringing the picture over here. This spot right about there is y equals 3, because we can see the y value at this point is 3. So if we're going to revolve this around y equals 4, I'd put 4 up here somewhere. I like to draw in a little, horizontal line there. I'll make it gray, something like that, just to show that that's the line that we are revolving around. Now, what's going to happen is we're going to take this thing and we're going to find what I've been calling big R. Unfortunately, they used big R as the name of the region that we're graphing. So if I'm going to call that guy big R, just don't get confused with the region being called big R. So that's our large radius, and that is going to come up and get revolved around that line y equals 4 and come back down behind and come back like that. However, we also have our little r, which is our distance to the closer curve. So we've got that guy, and I'm going to call him little r, and of course he's going to get revolved around, and what's going to happen is we're going to get this little shaded region kind of in between these two guys. That is our kind of like cross-sectional area, that little washer there, and we're going to have a whole bunch of those guys. Of course, this thing has a little thickness to it. Oops, back to a pencil there. This thing has a little thickness to it. Its width being dx. So we're taking infinitely many, infinitely skinny of these little washer-shaped things. That should have been in yellow. That should have been yellow, but I'll do it again. There we go. Kind of like that. And we're going to take a whole bunch of those discs and put them together and get kind of a sideways volcano-looking thing. Anyway, the formula for these guys is, of course, you don't have to draw any of that on the test if you just remember the formula. We are going to be integrating this area function. So the area, if we were kind of looking at that thing from this perspective coming in from the side, would be the area of the bigger circle minus the area of the little circle. And of course, the area of the big circle is pi times our big radius squared, and then we're going to subtract pi times the area of our, the area of our little circle, which is this guy in here, which is our pi times our little radius squared. So of course, if you factor the pi out, you get big R squared minus little r squared. Oops, little r, not pi. So that's our formula. We've got the we got the pi factored out, and our integrand is going to be what I'm writing as big R squared minus little r squared. I can do that because I've shown, well, you used to be able to see what I meant by that until I scribbled all over it. But again, big R was our distance from the axis of revolution, which is 4, down to this lower curve, the further curve. So that distance, the question is, how long is it from here to here in terms of x? Well, I know from the x-axis up to here is 4, and what we're just doing is we're losing this little part down here, this little red piece. Well, that red piece is the red function, which is x over 3. So the net distance, this green part in here, is 4 minus x over 3. So I'll go ahead and put that guy in there as big R. So we can do pi. Big R is 4 minus x over 3. And big R gets squared, so I square that. And then we're going to subtract little r squared. Let's get an expression for him. Little r has also been obliterated by my notes. Let's get a fresh color. I'll use the blue. So we're going from the axis of revolution down to the blue line. So of course, once again, the total distance from here down to the x-axis is 4, but we're missing this portion down at the bottom from there to there, which is known to be root of x. So the net is 4 minus root of x. So there we have it. Big R squared minus little r squared, integral with a pi out here, dx. Don't forget your dx. And not most importantly, but at the end, we are going from 0 to 9. These washers are going to move, are going to get smaller and smaller. The little ring is going to get smaller and smaller as we go through, so we can put our limits there of 0 to 9. And that's our final answer. And of course it says, write but do not evaluate, and you're very thankful that you don't have to evaluate that integral. Okay, so for part C here, find the maximum vertical distance between the graph of G and the graph of H between 0 and 16 on the x-axis. So I drew the graph kind of again because I did so much notating on that. Kind of wanted to get a fresh picture. So they're saying, where is the distance between the blue and the red, the maximum vertical distance between those two guys? Maybe I'll highlight that in yellow or something like that. Where is that distance going to be the biggest? So you might think, oh, maybe it's there, or maybe it's here. Then you realize it says, okay, 0 to 16. Well, geez, I think this distance is going to get bigger and bigger the further out you go. This linear function is going to keep growing, and the square root function is going to grow, but much more slowly. So the answer might well be way out at 16, but we're going to let the calculus show that. So what we need is an expression for that distance, doesn't matter where we are, I would say the distance would be, maybe I'll do it this way, the distance is root of x minus x over 3, because it's the upper minus the lower. Now, you might say, well, geez, when I get over here to the right side of this intersection, now it's going to be x minus 3 over, x minus 3 minus root of x. Well, here's the thing. I wrote d for this, but I didn't call it distance. I just said that I'm going to call that d. If that turns out to be a negative number, we would know that let's say it turns out to be negative 5. Well, that means the distance would be 5. So we can just look for when this thing has its largest absolute value. But it says find the maximum vertical distance between 0 and 16. So that to me sounds like find your absolute max on a closed interval. And if you remember that, if our closed interval is 0 to 16, what we want to do is take the derivative of the function and then set it equal to 0. That's going to be any x value that makes it 0 is going to be our critical number. And then if there's anywhere that makes it undefined, that's going to be a critical number. And all we have to do is check the y value of that function at the endpoints, which would be 0 and 16, and the critical numbers. So if we use our yellow d function here, d equals x to the 1/2, which is root of x, minus 1/3 of x. And the way you find a max or min is, again, just take the derivative, set it equal to 0. So d prime would be 1 over 2 root of x minus 1/3. Set that equal to 0. Already, I sense 0 is a place that would make this derivative undefined, but that's okay because we're going to wind up checking 0 anyway because it's an endpoint. Now we just have to solve this using your vast algebra skills. So you basically have, once you add 1/3 to the other side, you would have, or to both sides, you're going to have this. Then you can cross multiply and get 3 equals 2 root of x. And divide by 2, you get 3/2 equals root of x. And squaring both sides, you get x equals 9/4. So we have a critical number at x equals 0, because that made the derivative undefined right there. You have 9/4. So we're going to test the y values at those and our endpoints. Luckily, our endpoint is one of our critical numbers, so we can do d of 0. And if we test put 0 in the original function, we're going to get 0, which means our distance between the two is 0. Now, let's check 9/4. So d of 9/4, let's see, that's going to be the square root of 9/4, which is 3/2, minus 1/3 of 9/4. So let's see, that's going to be 3/2 minus 3/4, which is 6/4 minus 3/4, which is 3/4, I think. And then d of 16 is 16 to the 1/2, or the square root of 16, which is 4, minus 1/3 of 16. So that is 12/3, which is 4, minus 16/3, which gives us negative 4/3. So our d function gave us 3/4, which is probably, right around here. This thing has a distance of 3/4 of a unit. But then, as expected, out at 16, we've got a, net difference of, or the difference between the two values is negative 4/3, but that means the distance is 4/3. So your maximum distance is 4/3 at x equals 16. Again, understanding what's going on in that problem, it really makes the conclusion really easy. But there you go.